Welcome to the second and third lecture of this week. And in today's lecture, we're going to be handling the mathematical modeling problem. Usually when you have a control problem, the first thing that you do is to pass the system that you're working with into mathematical world. So suppose that you have an airplane. You really do not want to try arbitrary controllers on that airplane because its value is millions of dollars probably. So what you have to do is to obtain a very, very accurate mathematical model of the airplane first, and then apply your controller ideas on that model. And only if everything works fine on the mathematical model can we actually apply the same controllers on the actual system. So the first step of control, achieving control, is actually to mathematically model the system that we are going to be working with. So in this course we are going to have very, very basic mathematical models. I can actually tell you that this is also a problem in electrical engineering department as well. When we teach this course, as a slightly more advanced version of this course in electrical engineering, students usually complain about the mathematical modeling part because it is probably the most difficult problem they encounter in the control. The ideas are not usually familiar with, and probably you're going to be more so. So it can be a little bit painful, but I will try to make everything as basic as possible. And this is also a lighter version of the course that we are giving in electrical engineering. So therefore, we will try to be as basic as possible in EE381. So let us start with the topic of mathematical modeling. So in this course we are going to see some example systems, and these systems are going to be the following. So types of systems to consider. So we're going to be working with electric circuits and translational mechanical systems, rotational mechanical systems, and DC motor. So when I was giving the course alone in the last years, I was covering only the translational mechanical systems, and I was skipping the rest actually. But because we have combined the sections, one of the compromises that I had to make here is that we added the other topics as well into the course curriculum. So unfortunately you will have to tolerate me when I try to teach the other topics as well in this course. So here, electric circuits, you have seen examples of those before in your physics classes. Translational mechanical system. Translational means a linear motion. Okay, so translational mechanical systems are mechanical systems in which we have linear motion, no rotational motion. And rotational mechanical systems are, as the name suggests, are the systems, mechanical systems which would contain rotational or rotating bodies. And DC motor is a combination of all of the above three here. So DC motors in electrical engineering, we use them to actually combine the electrical world with the mechanical world. So if you have a robot, usually you will have many DC motors in it, and these DC motors are responsible to convert the electrical energy into mechanical energy. Okay? So we are going to consider three different mathematical models. So types of models to consider. So there are three mathematical models, three different types of mathematical models that are used in control. Actually, there are more, but we are including only three of them in this course. So the first type of mathematical models is the differential equations. I will abbreviate differential equation mathematical model with the capital letters DE. The second type of models is transfer functions. This is going to be represented by the letters TF. We will see immediately after writing this that transfer functions are nothing but the representation of differential equations in Laplace domain. And finally, the third type of mathematical model is called state space representations. And I will abbreviate this with the letters SS. So, unfortunately, we cannot neglect any of those. Even when I was giving the course alone, I was teaching all of these different types of mathematical models. So it is because in control, you are usually working with all of them with different control methods. So if you have a control application, sometimes transfer functions are more useful, and sometimes state space representations are more useful, and differential equations are the basis for both of these type of mathematical models. So unfortunately, it is impossible to neglect any of those mathematical models here. So we will consider all of them. So let us make an introduction to the mathematical modeling. So in general, we're going to have a system. So this system can be anything that we have the mathematical model of, or our aim is going to be to obtain the mathematical model for such a system. When I try to define a system, the first thing that I have to talk about is the input and the output of that system. So So input is going to be on the left and the output is going to be on the right. I will call the input as the signal U of t and the output as the signal Y of t here. So I have the input here and the output here. So when I talk about a differential equation mathematical model for this system, I am actually meaning something like this. So this is a differential equation model. I made it up. So it is not a model of a specific system that we have seen before, but a differential equation representation will be in general in the following form: a y dot minus by. So we are going to have an equation, and this equation is going to be linear. So there won't be any nonlinear function of y dot y double dot, for example. There won't be, in the differential equations that we are going to be working with, there won't be any y square, for example, which is a nonlinear function. And these coefficients would be constants as well in our applications. But in general, there might be nonlinear functions in a differential equation model, or these coefficients might depend on time, etc. So we are going to use, therefore, this simplified differential equation where these coefficients are constants with respect to time, and there won't be any nonlinear function of any of the derivatives of y or y itself. So a second order differential equation will be looking like this. I'm saying second order here because the highest order of derivative that I see here is the second order derivatives. These dots are representing the derivative orders. So this y dot is dy over dt, and y double dot is d square y over dt square. Okay? So we're going to shorten this derivative notation by putting dots on the top of the variables. So this is what a differential equation representation looks like. It contains the input and it contains the output and its derivatives. Sometimes we might have also the derivatives of the input as well in the differential equation. So this is another differential equation example. Y double dot is equal to U plus, let us say, C times U dot minus A Y dot minus B Y. This is also a differential equation type that we can work with. So here again, all variables are passed from linear functions. Derivatives is a linear function. Multiplication with a scalar, constant scalar, is a linear function, etc. And the coefficients are constant with respect to time. So this is also another differential equation type that we are going to see. But here I don't want to keep this here. I'm going to be working with the above one. But working with this one will be similarly easy. So this is our differential equation, and this is generally the first mathematical model that we are going to obtain. We are first going to write a differential equation of a mechanical system or an electric circuit. And then we are going to try to obtain the transfer function representation of the system. And this is just going to be the passing the differential equation into Laplace domain. Okay? So let us look at what a transfer function is. A transfer function is nothing but a differential equation represented in Laplace domain. Okay? So I'm going to take the Laplace transform of both sides of this equation while assuming the initial conditions are actually equal to 0. So what we mean by a transfer function, g of s, that is how we usually show the transfer function, how we usually name the transfer function. So this is my transfer function, and this is going to be defined as the ratio of the Laplace transform of the output to the Laplace transform of the input. All right? So this is what we call as a transfer function of a system represented by this differential equation. So we're going to be able to calculate the ratio of the Laplace transforms of the output to the input, and then that is going to be the transfer function of the system. So here, what we are going to do is we are going to pass the differential equation into Laplace domain. Using the derivative property. I will remind you what derivative property was, assuming 0 initial conditions. This part is important. So while trying to calculate the transfer function, we are always going to be assuming that the initial conditions of the system are all equal to 0. What do I mean by the initial conditions? Let us try to see. So remember, if a function f of t has the Laplace transformation capital F of s, then the derivative of that function f dot of t had the Laplace transformation s times f of s minus f of 0. Okay? So this is called the initial condition for the function f. So that is what we are going to be assuming to be 0 while calculating the transfer function. Okay? Therefore, when I assume that this is equal to 0, then f dot of t is just going to have the Laplace transformation as f of s. So we are assuming that the value of the function, I'm going to be assuming that the values of these functions u and y at time equals to 0 are all equal to 0. Okay? So then this is going to give us the simple representation here. F dot is going to have the Laplace transformation s times capital F of s. Okay? I can repeat the same idea for the double dot. f double dot of t. That has the Laplace transformation this times s. So this is the derivative of f dot. Okay, so f double dot is the derivative of f dot, but therefore by using this property, then I will have this, the Laplace transformation s squared times f of s minus f dot of 0, the value of the function at time t is equal to 0. So here we are going to be assuming that, again, this initial condition, the value of the derivative of the function at time t is equal to 0, I will assume that this is equal to 0 while trying to calculate the transfer function. Okay? So that is going to give us the simple rule, f double dot of t has the Laplace transformation s squared f of s. Okay? So we are going to have this simple property. So then, by assuming the initial conditions equal to 0, then taking derivative is just going to mean multiplication with s in the Laplace domain. Taking the double derivative is going to mean multiplication with s squared. And taking the nth order derivative is going to be the multiplication in the Laplace domain by s to the n. All right? So that is the simplicity of the Laplace transformation. All derivatives turns into multiplications with powers of s. That is why we are using the Laplace transformation to represent differential equations. So here let us apply this idea into our differential equation here. So that is going to give me y double dot. Let us take the Laplace transform of both sides. Then Laplace transform of y double dot is going to be s squared times the Laplace transform of y, and Laplace transform of u is going to be u of s minus Laplace transform of a times y dot. This is going to be a, I am using the linearity property of the Laplace transformation, and the Laplace transform of y dot, which is going to be s y of s. And finally, I have by, which is going to have the Laplace transform b times y of s. Okay? So this is the equation that we are going to be obtaining the transfer function from. What am I going to do here? I'm going to extract y of s only in terms of u of s, and then I will take the ratio of these Laplace transforms to calculate the transfer function of the system. Okay, let us do that. So when I take these terms to the other side, the terms related to y of s to the other side, I will have s squared plus as plus b times y of s is equal to u of s. And that is going to give me the transfer function g of s, which is by definition the ratio of the Laplace transforms of the output to the input. It is going to be y over u is going to be 1 over s squared plus as plus b. All right? So this is going to be the transfer function representation of our system. So now let us come to the state space representation. But before we start with the state space representation, I have to talk about the order of a system. Okay? When we look at the differential equation representation, we see the order of a system by the highest order derivative that the output has. Here, the highest order derivative that the output has is the second order derivative. Therefore, we are going to call a system represented by this differential equation to be of second order. Okay, so this is the differential equation representation of a second order system, because this is a second order differential equation. And how can I understand or how can I find out the order of a system from a transfer function? Look at the look at the transfer function representation of the system. This highest order derivative in the differential equation appears here by the s square in the denominator here. So as a result, the order of a system can be found out from the transfer function by looking at the highest power of s in that transfer function. Okay? Here the highest power of s is s squared in the denominator. We always look at the denominator. We always look at the denominator of the transfer function, and we look at the highest power of s in the denominator. So this is the second order transfer function, which means that we have a second order system. This is a transfer function representation of a second order system. This is going to be useful when we go into the state space representation. So the state space representation. So we have the differential equation here. I'm going to write it once more. Y double dot is u minus a y dot minus b y. This is a differential equation, and we will want to convert such a differential equation into a state space representation. What is a state space representation? So here you see that this is a second order differential equation. A state space representation is always a first order differential equation. So a state space representation, the highest order derivative in that representation is 1. We will only have first order derivatives in a state space representation. And we are going to be able to convert this equation into a state space representation, which will look like the following. X dot is equal to a times x plus b times u. Y is equal to cx plus d times u. This is what a state space representation is looking like. So you see that now I'm using a variable called x. This is called the state vector. Okay? X is called the state vector. And state vector is usually an element of Rn, and n is the order of the system. Okay? So here, what does this mean? This means that if I want to find a state space representation for this system, then n is going to be equal to 2, because this is a second order system. So x, then, the state vector is going to be a vector with 2 elements. And the elements of the state vector, so elements of x, are called state variables. These are the variables that summarizes the state of the system at each time instant. So you see that when going from differential equation to state space representation, I am reducing the largest order of derivatives here. Here the largest order derivatives is 2, and when I go into the state space representation, I'm actually reducing the highest order derivative to 1. But then what is happening here is that then if I want to write a first order differential equation for a second order differential equation like that, then what I have to do is to increase the dimension of the variable that I'm working with. So here, while going from here to here, we start using the variable x, and we reduce the derivative order from 2 to 1, but then we will have to use a vector variable. Instead of a scalar variable y, I need to use a vector variable here in this differential equation, and the size of that vector variable should be the derivative, highest order of derivative here, which is 2 in this example. So we have these state variables. As a result, the most important issue when we go from differential equations to state space representations is going to be the selection of these state variables. You can choose the state variables in infinitely many ways. there are infinitely many different ways to select state variables. And we are going to see actually in this lecture that every selection of state variables, every different selection of state variables is going to result in a different state space representations. So when we talk about state space representations, there is no uniqueness. Okay? Corresponding to a single differential equation, corresponding to a single transfer function, there might be there are actually infinitely many state space representations, depending on your state variable selection. So here, I have a vector variable here. X dot is, so x is just a vector with n elements, and x dot is a vector again with n elements containing the derivatives of the state variables. Okay, so this is a vector. So x dot is again in Rn, and then this A should be a matrix, and its size is going to be, A is going to be in Rn by n. Okay? Because when I multiply it with an n vector, it needs to give me an n vector here on the left. B is going to be a single vector, so this is going to be in Rn by 1. And C is going to be a horizontal vector. It is in R1 by n. And finally, D is just a scalar. It is just in real numbers. All right? So here, just as an example, I'm going to choose some state variables here, and then I will obtain a state space representation for that differential equation. Okay? You will see that the procedure is not really difficult once you select your state variables. So we usually, when we have a differential equation like that, we usually select our state variables as y and its derivatives. So for this example, I'm going to choose the state variables as the following. If you don't understand here, we're going to do the same thing in this course over and over. And if it is not clear now why I select this state vector like this, it is going to be clear in the very recent future. So don't worry, please. So I will choose this first state variable as the output y, and the second state variable as its first order derivative. So this state vector is then going to be a vector with two elements, which is composed of y and y dot. Then I'm going to be writing x dot here. So let us write what x dot is. It is just going to be the element-wise derivatives of these two terms. So derivative of y is going to be y dot, and derivative of y dot is going to be y double dot. Okay? Now let us try to find the state space representation corresponding to this state vector selection. Okay? So we see here that what we are trying to do here is that we are trying to write the derivatives of the state variables as a linear combination of the state variables and the input. Okay? We try to write, while trying to obtain a state space representation, we are trying to write the derivatives of the state variables as a linear combination of the state variables themselves and the input. Similarly, we are trying to write the output variable as a linear combination of the state variables and the input here. We are going to use this idea while trying to obtain ABCD. Finding a state space representation means finding ABCD matrices and vectors. All right? So if I write here x dot, that is going to be, I will have a 2 by 2 matrix here, x plus b is going to be a vertical vector, u, and y is equal to, this is going to be a horizontal vector like this, and d is going to be just a scalar, u. So we need to find what this matrix is and what these vectors and this scalar are. All right? So let me write x dot here. X dot is, as you see here, y dot and y double dot. And x is here, y and y dot. So this is my x. Now let us try to obtain this A matrix and the B vector. So in order to be able to obtain the first row of the A matrix, I will try to express the first row of x dot, which is y dot, as a linear combination of the state variables and the input. Okay? I will try to, in order to be able to obtain the first row of the A matrix, I'm going to write y dot, the first row of x dot, as a linear combination of y and y dot and the input. Okay? I need to write the coefficients of that linear combination to here, and the coefficient of the input here. So the task is really simple. Express y dot as a linear combination of y, y dot, and u. Okay? This is really a trivial linear combination, okay? Because y dot is just one of these variables here. So I can express y dot as a linear combination of y and y dot by multiplying y with 0 and multiplying y dot with 1 and multiplying u with 0. Okay? So what did I do here? I expressed y dot as a linear combination of y, y dot, and u. And what is that linear combination? Y dot is 0 times y plus 1 times y dot plus 0 times u. Okay? So then I get the equation y dot is equal to y dot, which is a trivial equation. But we see that we get the first row of the A matrix and the first row of the B vector here using this expression. Now let us look at the second row of A and B here. The second row of x dot is y double dot. Now what I have to do is express y double dot as a linear combination of y, y dot, and u. And how can I do that? I'm going to go back to my system definition. This is my system definition, and my system definition, the differential equation, actually tells me what that linear combination is. This is expressing y double dot as a linear combination of y, y dot, and u. All right? So then what should be the coefficient of y in expressing y double dot in such a way? So we see that the coefficient of y, while trying to express y dot as a linear combination, is minus b. So I will put minus b here. And the coefficient of y dot, we are multiplying this vector with the matrix like that. So y dot is going to be multiplied with this column. Okay? So the coefficient of y dot is going to be minus a. And the coefficient of the input is going to be just 1. All right? So you see that we have already found the A matrix and the B vector here. All right? And what about the output equation? So this is called the state equation. And this is called the output equation. A state space representation is composed of both state equation and the output equation. And we need to find A, B, C, D here. So here, what about the output equation? The output equation wants us to express the output as a linear combination of the state variables and the input. Okay? So y, what is that coefficients of that linear combination? Express y as a linear combination of y, y dot, and u. This is again a trivial task here. Y is just 1 times y plus 0 times y dot plus 0 times u. Okay? So I will put here the coefficient of y is 1, coefficient of y dot is 0, and the coefficient of the input in this equation should be just 0. Okay? So you see that we have found the state space representation, and in this equation I have a vector variable with a state vector with two elements, and the highest order of derivative is 1, but the cost for that highest order derivative, reduced highest order derivative, was that we need to work now with a vector variable, which is the state vector. All right? So here, this is my A matrix, this is B, this is C vector, and this is our scalar D. So this completes my introduction for the different mathematical models that we are going to see. Now we're going to apply these ideas on example physical systems. And the first type of physical systems that we're going to be working on is going to be the electric circuits. So just as in the industrial engineering, we have in electrical engineering, we have different areas of research. And some of these research areas, some of them are more mathematical than the others. Some of them requires more physics than the others, etc. So as an electrical engineer, I can actually tell you that I really didn't touch any electric circuit for the last 20 years. So I'm working I'm making research on a very, very mathematical area of electrical engineering, so therefore I have forgotten probably all of the electric circuit classes that I have taken before. But there are some basic information I still remember to carry on such type of analysis. So I'm saying this because not all electrical engineers or not all professors in electrical engineers are comfortable with electric circuits in the same way. I'm one of them who is not comfortable with those topics. But still, electric circuits would provide us a very, very interesting systems that we can work on mathematical modeling. So here I will try to give you the basic ideas that you can use in electric circuit analysis, and the circuits that we are going to encounter in this course will not really be complicated. Probably the most complicated circuit that you are going to be working with is going to be a series connection of resistors, inductor, and a capacitor. And that is what I'm going to apply in this lecture, the ideas that we found. So first I will write the components of an electric circuit, and I will write their terminal equations. So you would probably remember those from high school or from your physics classes in the first year. So the first element is resistor. And it is going to be shown with such a notation. The voltage that we apply is shown by V, and the current that we get at the result is called I. And the resistor equation, terminal equation, is nothing but the following. V is equal to the resistor value, resistance value times I. All right? So this is shown, resistance is shown by the letter R. And then we have the inductor. In that case, we will have a slightly different notation, and I will show the inductor with the letter L, inductance value with L. We have the voltage V, and we have the current I here. And the terminal equations of an inductor is the following. V is equal to L times di over dt. Okay? So the voltage that you apply is going to be the time derivative of the current times the inductance. Or you can here say that the current that you get is going to be the integral of the voltage that you apply. All right? And we have a capacitor. So we will show the capacitance with the capital letter C, and the terminal equations is going to be the current that you get is going to be just C times the derivative of the voltage. All right? So unfortunately, you will have to know these terminal equations of the electric circuit elements in this course. In addition to these elements, we have one more fundamental circuit element that you have probably not encountered before. But it is really nothing complicated. It's called a transformer, and in Turkish it is trafo. So when you have a electric distribution systems from the dam, from the hydroelectric dam, you get an electric current and electric voltage which is very, very high. So it is thousands of volts that you get into a city from a hydroelectric terminal. So what you do in order to use it in your homes is that you use a transformer in order to reduce the voltage from thousands of volts to hundreds of volts. Okay, so you must know that in our houses we are using 220 volts voltage. Okay. So here a transformer is just such a device which reduces or increases the voltage. So we show the transformer with a notation like this, and here we apply a voltage on this side, which is V1, and we get another voltage on the other side. This is V2. Okay? So then we have a current I1 on this side, and we have another current I2 on the other side. So, for example, this might be the high voltage part of the transformer, and this might be the low voltage part of the transformer. So you give the high voltage input here, and the transformer, trafo, gives you a low voltage on the other side, which is what is required in our houses. So here, there is only a single, there are actually double parameters, but it is effectively a single parameter. So we have a turns ratio for the transformer. This is called a turn ratio. In general, a transformer is something like this. So it is just an iron core, and it is looking like this. I'm not sure I will be able to draw this in a fine way now, but it has a coil on this side, and it has another coil on this side. Okay, and this is the terminals. It is these terminals on this side, and the other terminals are here. So there is a winding here. There are some coils that are wound here around the iron core here. Okay, and in the transformer notation, we show the number of turns of this coil as N1, and the number of coils in the turns on the other side as N2. In transformer theory, if you look at it in a mathematical model, then the voltage at each side is actually proportional to the number of turns of the coil on each side, on the corresponding side. So if I try to write the terminal equations of the transformer here, I'm actually going to write the following. V2, the voltage on this side, is going to be proportional to the number of turns in these coils. Okay? It is going to be N2 over N1 times V1. So if N2 is larger, then this ratio is going to be larger than 1, which means that the voltage here is going to be larger than this one. And due to the conservation of power, we have the current relationship, which is reverse. Okay? So I have I1 here. If you have N2 over N1 ratio here, we have N1 over N2 in the current equation. Okay? so that when you multiply the current and voltage here, it is going to give you the electrical power. The power on this side is going to be equal to the power on this side. This element is called the ideal transformer. Okay? And the terminal equations are given by these expressions. So the voltage relationship is proportional to the number n's here, and the currents are inversely proportional to the numbers n. This is all you have to remember here. You need to remember the mathematical model. And how do we obtain the mathematical model with an electric circuit? So in electrical engineering, we have an important guy who has first theorized those laws that we use in electric circuits. And these are called the Kirchhoff voltage and current laws. Voltage and current laws are used to obtain the mathematical model. So these are all of the elements that we are going to use in electric circuits, and most of the time we won't use the ideal transformer here, but resistor, inductor, and capacitor might actually appear in our models. So now I'm going to be solving a simple electric circuit example, and the task is going to be obtaining the mathematical models for that simple electric circuit. And what do we mean by models? We mean the differential equation, transfer function, and the state space representation. So let us look at an example. So I have an input voltage here, that is V of t, and in this circuit I have a resistor, and I have an inductor, and I have a capacitor. Okay? It is a very, very simple circuit. So I don't think that in this course you're going to see a more complicated example of an electric circuit. So please try to tolerate us a little bit in this circuit stuff. So I have L and I have C here. I will define some voltages. This is the voltage on the capacitor, VC. This is going to be the voltage on the inductor, VL. And this is going to be the voltage on the resistor, falling on the resistor. And I will define some currents. This is going to be the current on the resistor. This is going to be the current on the inductor. And I will have the current on the capacitor. All right? So we have just these variables. So let us write what our task is. Our task is find differential equation, transfer function, and state space representations. That is our task. Actually, now I have defined a mathematical modeling problem. So we need to find a mathematical model of a physical system. But there is a very, very important thing missing in the statement of the problem now. Okay? When you talk about a system, when we talk about a system, we need to always define, or you should be always given what the input and the output of that system are. Okay? So here in my statement, these are all missing. Okay? So without the definitions of an input and the output of the system, this problem is not really complete. It is a meaningless problem because we don't know what the system is. What is the input of the system? What is the output of the system? So these are defined for us. Or you need to define them before working on this problem. So I'm defining my input to be the voltage V of t, voltage on this side, it is a function of time, and the output, I define it to be the capacitor voltage, okay, Vc of t. All right, this is also a function of time, and now the problem is complete. I know what system I'm considering. I'm considering an electric circuit system with the input voltage V of t and the output voltage Vc of t. Sometimes the problem can be different. Then I would have a different problem. If I define the output to be the capacitor current, then I would have a different problem statement. Then I would have a different problem because then I have a different system. So without these definitions, the problem is meaningless. So now let us try to obtain the equations that are satisfied by such a system. This notation shows the ground in this system. So this is, here I have a 0 volts. All right? It is not really important. For this course sake, I can remove this one as well. So here, let us try to write the equations that are satisfied by the variables. So the first thing is going to be, I'm going to write the terminal equations of the elements. And these are going to be these three equations actually. So the resistor voltage is R times IR, okay? R times the current on the resistor. So I have the inductor voltage is L times DIL over dt. I'm just repeating those terminal equations, doing nothing complicated. So I have, finally, the capacitor current, IC, is C times dVc over dt. Okay? I have written the terminal equations of the elements. Now what I have to do is to write the relationship between the variables here. So you see here that I have the input voltage here, V of t, and I have a voltage here, and a voltage here. For the circuit to be an actual circuit, actually, the summation of this voltage, and this voltage should be equal to the source voltage. It should be equal to the voltage of the source here. Okay? Then, therefore, my first equation is going to be the following. If I sum VR plus, if I sum the voltage on the inductor, if I sum the voltage of the capacitor, then this is going to be equal to the input voltage. Okay? In electrical engineering terminology, this is called Kirchhoff's voltage law. Or sometimes we call it KVL. Okay? So summation of the voltages here should be equal to the source voltage. And what about the relationship between the currents here? Here I have a single wire, and on this single wire I have three different current variables defined. Okay? But on a single wire, all of these currents should be equal to each other. Okay? That is going to be IR plus IL. Sorry, these are equal. IR is equal to IL. This is equal to IC, and they should be equal to a single current I of t. All right? In electrical engineering, you can call this as the Kirchhoff current law. So on a single wire, we have only a single current value. This is called Kirchhoff's, or it can be derived from the Kirchhoff's current law. Okay? So these two equations would give us, so these are the mathematical modeling equations that I can write, and these are going to give us at the end what the differential equation representation is and what the transfer function representation and what the state space representation is. We're going to derive all of the mathematical models from this set of equations. So now let us start with the differential equation representation. I will erase this part to be working comfortably. So here, what is the differential equation representation? I need to find the differential equation that relates the input and the output variables. Okay? So I need to find a differential equation that is relating, that is giving us the relationship between the input and the output variables. So I have to find the differential equation that actually involves the input variable and the output variable. And I need to get rid of all other variables here in order to be able to find the differential equation representation for this system. And here, I can actually see that I can start with the first equation here because it already has VC in it and it already has V of t in it, the input variable. So if I can get rid of this VR and VL here, then I'm done with the differential equation representation. Okay? So we start with the first equation, VR plus VL plus VC is equal to V of t. And in order to be able to get the differential equation representation, I'm going to be getting rid of these variables VR and VL. Okay? So what does it mean? What is getting rid of means? It means that I need to be able to write the resistor voltage in terms of the capacitor voltage and or the input voltage. And I need to be able to write VL in terms of VC or V. All right? So let us look at VR. VR is R times IR. Okay? I can actually try to write this in terms of VC. How can I do that? The interesting thing here is that this is R and IR is equal to the capacitor current in this electric circuit. So here instead of IR, I can write IC here. And what is IC? IC is C times dVC over dt. It is in terms of VC, as you see. So it is R times, instead of IC, I write C times dVC over dt is nothing but VC dot. Okay? So I write just VC dot here. So I found my relationship between VR and VC. This is RC VC dot. I'm going to be using this equation. Let us now try to apply a similar idea to the voltage VL. I need to get rid of this one as well in the differential equation representation. So VL is, I know that from the terminal equation I have this one. It is L times d over dt IL. And I know that IL is equal to IC as well. All right? And this is going to be therefore L times d over dt IC. And I know that IC is C times dVC over dt, C times VC dot. Okay? So this is L times d over dt C times VC dot. C is a constant with respect to time, so when I take the derivative, I only need to take the derivative of VC dot, which is changing with respect to time. So VC dot, if I take its derivative, C is going to come out LC, and the derivative of VC dot is going to be VC double dot. Okay? So that gives us our second equation. VL is equal to LC VC double dot. Okay? Now all I have to do is to take these equations and substitute them into my main equation. Okay? Let us do that. VR is RC VC dot plus VL is LC VC double dot plus Vc is equal to V of t. Now this is a differential equation that I require. Differential equation relating the input to the output, or just vice versa. So here I'm going to change the places of these terms just a little bit. LC Vc double dot. I'm going to order the derivatives here. So I have RC Vc dot plus Vc is equal to V of t. And I'm going to divide both sides with LC to leave the highest order term alone here. So I have Vc double dot plus divide RC by LC. It is going to give you R over L Vc dot plus 1 over LC Vc plus 1 over LC V. So this is my differential equation representation. The others are also the differential equation representation, but I really like to work with a differential equation in this form where the coefficient of the highest order derivative is 1. So this is my differential equation representation. Now this completes this part of the problem, and the second part is going to be to find the transfer function representation. Remember, so I start with the transfer function. Remember, the transfer function representation is nothing but finding G of S, which is the ratio of the Laplace transforms of output to the input. Okay? Here, the output is the capacitor voltage. It is defined. So this is Vc of S. And the input is the source voltage, V of t. So its Laplace transform is V of S. Okay? So this is going to be my transfer function. This is my definition. And this is the result that I need to find in this specific problem. All right? So I need to find Vc of S divided by V of S. And that is going to be my transfer function representation for this system. So here let us use the differential equation representation for that purpose. All right? I'm going to pass this equation into Laplace domain while assuming that the initial conditions are 0. So therefore, the derivative means multiplication with S. Double derivative means multiplication with S squared in Laplace domain. So here let us do that. If I take the Laplace transform of Vc double dot of t, then it's going to be S squared Vc of S. That is plus, I have R over L, which is a constant, linearity property of the Laplace transformation, and Vc dot is going to be S Vc of S, plus 1 over LC, it's just a coefficient, and Vc of t, its Laplace transform of its Laplace transform is Vc of S, and I have the last term here on the right. It's going to be 1 over LC, and I have V of S. Okay? Then in order to be able to find this ratio, I will leave Vc of S alone here. So I will take Vc of S parentheses, S squared plus R over Ls plus 1 over LC. Vc of S is equal to 1 over LC V of S. And if you calculate this ratio then from this equation, you're going to get the transfer function representation. G of S is Vc of S divided by V of S, and that is going to be 1 over LC divided by S squared plus R over Ls plus 1 over LC. Okay? So this is our transfer function representation. So how are we going to use such a representation? Transfer function representation is useful because of the following. From this equation, I can actually write the capacitor voltage, Vc of S, as the transfer function times V of S. Okay? The output of the system is always the transfer function of the system times the Laplace transform of the input. The output, Laplace transform of the output, is always the transfer function of the system times the Laplace transform of the input. Okay? So what happens if I choose V of t? Suppose that my input voltage is the unit step function. So it is 1 volt for t larger than or equal to 0. Okay? In that case, this is the input voltage. It is 0 before time t equals to 0, and it is equal to 1 after time equals to 0. Okay? Then what is the Laplace transform of the input? Then V of s is going to be 1 over s. We have seen that the unit step input has the Laplace transformation 1 over s. Then what is the Laplace transform of the output for this system? For this specific input of the system, what is the Laplace transform of the output? Let us try to find that. Vc of s is going to be, V of s is 1 over s, so I have 1 over s, times the transfer function, 1 over LC, s squared plus r over ls plus 1 over LC. Okay? So you see, this is the Laplace transformation of the output for the step input, unit step input. For constant input voltage, this is the output Laplace transformation. So you can actually try to find the time function corresponding to this Laplace transformation. There is going to be a constant term, so A over S, and depending on whether the roots of this polynomial are complex or real, I will have some other terms. Okay? There will be a constant in the output, a constant voltage. In addition, I will have two exponentials here, or sines and cosines. There will be oscillations, as we have seen in the earlier lectures. So by just knowing the transfer function, I can multiply that transfer function with the Laplace transform of the input, and then I know the Laplace transform of the output. All right? And I can actually try to understand the characteristics of that output by looking at the poles of that Laplace transformation. And pole at 0 means a constant, and double poles at some locations means either two exponentials or sines and cosines with exponentials in the front. Okay? So this transfer function idea gives us to understand the behavior of the output for different input types. So that finishes the transfer function representation, and the final thing that I'm going to do is to find the state space representation. I'm going to apply a very, very similar idea here. So this is the differential equation that I want to find a state space representation for. This is very similar to our earlier example with y as the output. So that is what I'm going to do. In the earlier example, I have chosen my state variables as y and y dot. Here, I will be able to do the same. But why am I choosing two state variables in this case? The reason is that this system is, again, a second order system. The highest order power of S is 2 here in the denominator. That means that this is a second order system. That means that I need to have two state variables in the state vector. And this is the differential equation that I want to represent using state space representation. And I'm going to do the following. I will choose my x as Vc and Vc dot. Okay? Then I'm going to find a state space representation in a similar way that I did in the introductory example here. So here, this is my state definition in this case. And I have x dot is equal to a times x plus b times u, and y is equal to c times x plus d times u. Here the input, what is the input in this example? It is the input voltage. This is V of t. Okay? State is given as Vc and Vc dot, and the derivative of the state, what is it? It is the derivatives of these two elements, Vc dot times, and not times, Vc double dot. Okay? Derivative of Vc is Vc dot. Derivative of Vc dot is Vc double dot. Okay? And the output in this example is just Vc of t. Now let us find the state space representation for this system. In order to be able to find the first row of A and B, I need to express the first row of x dot, which is Vc dot, as a linear combination of Vc, Vc dot, and U. Okay? This is a very, very trivial linear combination. Vc dot is 0 times Vc, 1 times Vc dot, and 0 times U. Okay? And let us look at the second rows. So I have Vc double dot. I need to express it as a linear combination of Vc, Vc dot, and U, which is V. So I'm going to go back to this differential equation. Express Vc double dot as a linear combination of Vc, Vc dot, and V here. All right? What is it going to be? What is going to be the coefficient of Vc? It is going to be, Vc dot is going to be, I will take this to the other side to express Vc double dot as a linear combination of this, this, and this. So the coefficient of Vc expressing Vc double dot is going to be minus 1 over LC. Coefficient of Vc dot expressing Vc double dot is going to be minus R over L. And finally, the coefficient of the input, which is V, expressing Vc double dot, is going to be plus 1 over LC. All right? And this completes A and B matrices. Let us look at C. So here the output is Vc of t, and it is the first state variable. I need to express the output as a linear combination of state vector elements and the input. So this is going to be 1 times Vc plus 0 times Vc dot, and there is no input in the output. So there is no input contribution in the output, so I will have a 0 here. So this completes actually the task of finding a state space representation for this system. So as I told you, so here I will first ask the following question: could I have chosen the state vector x with two elements, with the following elements, Vc and Vc double dot? Could I choose state elements Vc and Vc double dot? I'm trying to rationalize this state vector selection here by considering such a, in effect, nonsense example. So here, what is a state space representation doing? State space representation is expressing the derivative of each state variable in terms of the state variables themselves and the input. Okay? If I choose this state, then I need to express derivative of Vc in terms of the state variables themselves and the input. Derivative of Vc is Vc dot. Can I express Vc dot as a linear combination of Vc, Vc double dot, and the input V. You will see that you won't be able to do it. Here it was easy because VC dot is just the second state variable. So I can express the derivative of the first element as a linear combination of the state variables here. What about the second element here? I need to express the derivative of the second variable, which is going to be VC triple dot. VC triple dot, I need to be able to express it in terms of VC, VC double dot, and the input V. Here, in none of my equations, I have only a single differential equation there, and in none of my equations, I have the triple dot of VC, okay? So therefore, I really will not be able to work with such a state definition. So for a state definition to be working, what I need to have is that I need to be able to express the time derivative of each variable as a linear combination of those variables in addition to the input. Okay? So here it is really obvious. VC dot is already one of the state variables, and VC double dot can be expressed in terms of these variables plus the input. Okay? That is why this idea is always working. So but actually there are other state definitions which would work for this system as well. Okay? I have told you at the beginning of the lecture that state definitions are not unique. As a result, state space representations are not unique. So if I choose another state definition which works, for which I can actually obtain ABCD, then that is also a valid state space representation. So let me erase this part, and just as an example, I will choose another state definition, and then we'll show you that it is going to give you another state space representation. So let me write this as a note. State space representations are not unique, or state space representation is not unique. Okay? If we choose different state variables, which means a different state vector, then we get a different state space representation. So in classical electrical engineering education, students are taught the following. So this finishes this node here. EEs are taught to choose capacitor voltages and inductor currents as state variables. Okay? So that is what I'm going to try to do now. So now instead of choosing my state variable as VC and VC dot, I'm going to do the following. I will keep my first state variable as VC, and I will choose my second state variable not VC dot, but I will choose it as the inductor current, IL. Okay? And this is the common current, common single current in the circuit. Okay? So let us try to find the state space representation corresponding to such a selection. This is my new definition of the state vector, and I'm now going to be finding the state space representation corresponding to this state selection. So the first thing that I'm going to start is to write what the derivatives of these variables are in terms of the same variables. Okay? So I will start C times VC dot. Remember, in the capacitor equation, this is going to be equal to the capacitor current. In the capacitor terminal equation, IC is C times VC dot. Okay? So I write C times VC dot is the capacitor current. But the capacitor current is nothing but the inductor current here in this example. All of the currents are equal in that example. So this is equal to IL. So this gives us our first state equation, C times VC dot. I'm going to show how this can be converted into a state equation. This is IL. So you see that in this equation, I express the derivative of the first state variable in terms of the state variables and the input. And here I have the only state variable on the right hand side, which is IL. Now let us try to do the same thing for the second state variable. So I have L times IL dot. In the inductor terminal equations, L times IL dot is nothing but the inductor voltage, VL. Okay? And what is the voltage falling on the inductor here? I can write the voltage falling on the inductor as the source voltage minus the voltage on the resistor minus the voltage of the capacitor. Okay? Inductor voltage here is nothing but V minus VR minus VC. Okay? So I have this is V minus VR minus VC. Okay? VC is already one of the state variables and V is my input. So here the only thing that I have to take care here is this VR, which is neither a state variable nor an input of the system. Okay? So if I can take care of that variable, then I'm done with the second state equation. So this is going to be L times IL dot is equal to V, I can keep this term because it's input, minus instead of VR, I write R times IR. But IR is equal to IL, which is one of the state variables here. So this is going to be R times IL minus VC is already one of the state variables. So this is my second state equation. So now let us try to write our state space model here. I will first write X dot is equal to AX plus BU. Here, U is the input V, and X is VC and IL, and X dot is VC dot and IL dot. Okay? As you see, I'm always doing the same thing over and over. Express VC dot using your equations in terms of VC, IL, and the input V, as a linear combination of VC, IL, and V. So VC dot from this equation, you see that it is 1 over C times IL. So I will put 1 over C here times IL, and there will be zeros everywhere else. And in the second row, I have IL dot. Express IL dot as a linear combination of VC, IL, and V. Okay? And then I will use this equation. Express IL dot as a linear combination of VC, IL, and here V. All right? So IL dot is, what is the coefficient of VC here in IL dot? As you see, it is going to be minus 1 divided by L. Minus 1 over L here. Okay? And what else? What is the coefficient of IL? It is going to be minus R over L. And finally, what is the coefficient of V in IL dot? It is going to be plus 1 over L. This is going to complete the state equation. And finally, I am going to be writing the output equation, which is going to be very, very easy. Because output is just VC here. So Y is equal to, I will have C vector X plus U. This is now V, and this is VC and IL, and this is VC. Express VC as a linear combination of these elements and the input. The linear combination is simple. It is just 1, 0, 0. So you see that although the output equation is the same, because the first element did not change in our state, the state equation changed a little bit, and I get a new state equation for this new state definition. And actually, both of these state space representations are corresponding to the same system here. So we see here that for a single transfer function, for a single system, for a single differential equation, we might have multiple state space representations depending on our state vector selection. So now I'm going to give a break, and in the next lecture we are going to see the mechanical systems.